we can I have a couple of announcements to make regarding the seating arrangement for the quiz which is on Monday. Seating arrangement is very much decided by the official announcement that has come, but since the PhD scholars are put in 2 rooms, I just want to make sure that they all sit in 1 room. So this place would be MSP 40. They all PhD scholars. Plus other department students. This includes only applied mechanics, catalysis. There is a separate category, so that would come in 355. So all PhD scholars, pretty much they belong to chemical engineering. Plus other departments which include basically only applied mechanics. So if there are any others, then they can sit here. MSP 355 will be all MTech students. This is as per the official notice. So all MTech students are in the same room. On top of it, this is CHE plus all CA catalysis students plus all mass MS students. These are basically chemical engineering. I don't think there are any other MS students from other departments. So this would complete the seating arrangement. There will be 2 rooms. Basically, MTechs, MS and catalysis they are in 355. Confusion will arise because the MS scholars are put in 2 different rooms. So I want all of you to sit in the 355 because a bigger room, so I hope there should not be any problem in accommodating. The same thing, 240 PhD students have come or put in 235 also, but I want all of the PhD students who have registered for this course to sit only in 240 plus the applied mechanics, whoever is still left registered. So, are there any questions on this seating arrangement? So I don't want you roaming around here. There are 4 rooms. You should be clear which room at least you should be sitting. Then regarding the material that you should know, your quiz will be a closed book and notes. No formularies or anything will be allowed. And invariably, I will give all possible formula that are required, not all possible formula, but all formula that are required in the quiz would be there in the quiz sheet itself. But I still think you should recap and be ready to use some of the basic vector and tensor operations. So I just review it for you because I don't. It's very awkward, and you might not have enough time to finish the quiz if you are just looking at the formulas that are given there and trying to apply it. So I basically first it's important to categorize these operations so it's easy for you to remember. So you take 2 vectors, operations involving vectors. I can think of 3 operations. The repeated index summation convention will be used in the quiz, right? So it is understood that we will be using it. If there is a confusion somewhere, as I said, AI, whether it refers to trace or the I element, then it will be mentioned in the quiz sheet. Whether invariably repeated index is not being followed, then it will be mentioned. If it is nothing is mentioned, it's understood the repeated indexes are somewhere, right? So 3.3, and also I put an underscore here, but you might have seen in the assignment. Typically, I have used a boldface, lowercase for vectors, and uppercase, boldface for tensors, and scalars will simply have, italics probably, that's what it would be. So it's very easy to identify, but invariably it could be made clear in the quiz paper. If there is a confusion, you should be thorough with the notation that we have used. I'm not going to change anything. Okay. So A cross B. One way to remember this is simply as a determinant. Or this can simply be written as epsilon ijk, from which I can easily pick the ith component or whatever component you want. We have seen how to manipulate the epsilon to get whatever component that you want. Right? So this is what it is. The third one, I am going to write just the ij element, B-I, B-J. Right? So operations involving vectors and tensors. These are not exhaustive, I'm just writing it from memory, but you should just go and repeat. These are things that we commonly encounter, especially the dot product and this would be like the ith component. And then there is a whole set of operations involving the gradient operator, right? That is the gradient operator. Divergence of with respect to a vector would simply be ai comma I. So I will be using the comma I in the organic operator. Simply means d by dxi of ai. So again, it's repeated index summation. Then divergence with the tensor. That's a scalar. The tensor is, we have seen AJI comma J, the ith component. Okay. It's important that you are conversant with these. You work through the assignments you could be. So these are the divergence. Then the gradient of a scalar would be the ith component. Okay. Gradient of a vector, we have also seen it's a tensor. General, right? So the ij element would be aj comma I. Right? If you want then what else? We have also seen a cross product. That's a little bit more difficult to remember, but it's easy to remember the cross product. You remember it as this way, as a determinant. Okay. Remember that then you use the epsilon formula that you should know for the determinant of any matrix. So this would be epsilon ijk ei, right? So you can easily write the ith component from this. So d by dxj, right, of ak. This is actually easier to remember here because the ak comma j is, when you remember this, then the ith component can be easily written as ith component of the curl of a vector. I don't know if there are any other operations, but these cover the basic operations. Certainly these we have used quite widely. These are some of the operations that we have used. By no means this is exhaustive, but some of these formulas you should have, you should have reviewed it and you should be ready to use it. But there will always be a guide in the quiz sheet which you can refer to just to confirm whether the formulas are correct or not. But I don't depend entirely on that. Are there any questions on what you should know in the quiz? Yes. Equations of motion, yeah, you should. I remember all of them, so but I think you should equation of continuity. difficult to remember the equation of motion. So that will be the formula for subtract. All these I expect you should, but it would not be such a stringent test of your memory. I assume that you are familiar with these equations and you have derived them. You are familiar, right? So this is not all that you need to do. But basically, I don't think you have to remember anything. In sense of having to memorize, if you have followed the lecture, some of these equations should clearly be very easily accessible to you. It will always be, because in a closed book, there's always a doubt, how much you have to remember. I think you should come simply, prepare some of these basic operations, and I'm sure you will find no problem. I'm sure none of you will lose any points just because you could remember some formula. That will not be the case. That much I can assure. In the worst case, you can always ask me that question. If it's really, I think, necessary, I will announce it for the exam. As I can simply say that you're supposed to know it, but I'm very sure that it's very unlikely to happen. Any other questions? This I think you have to remember, because I often have a problem of students who are not supposed to be in a particular room, right? Going here and there, and then the quiz is always a problem, because the 8 to 8:50 we have to wrap it up and then leave the room free for the next class. So I expect that you will be responsible. So I would say finally, you ask me what do you have to remember, only this. We've been looking at this flow between parallel plates, and this is the coordinate system that we have defined. We assume one-dimensional flow, and further we assume to be a function of x alone. The fact that it doesn't depend on z follows from the continuity equation, but on top of it, we'll assume that there is no variation of b z with respect to y. So b z will depend only on x, and then we wrote down the equation of motion, the three directions, and finally, based on the boundary conditions, here we said this plane would be moving with a velocity u without any commitment to. So if u is greater than 0, then the plane is moving in the positive z direction. If it is negative, then it's moving in the negative z direction. So, but for deriving, so the boundary conditions are x equal to 0, b z equal to 0, and x equal to k, b z equal to q. So the sign of u would take into account which direction the plane is moving. Then with these the solution can be easily shown to be given by this, right, that minus p naught prime, or p naught prime is actually dt by dz is going to be a constant. We pointed out that the plate is not moving at all. The bottom plate is always assumed to be stationary. The top plate is not moving at all. So clearly a pressure drop in the z direction will drive the flow in the z direction. So we assume that for all practical purposes, there is no generality lost by assuming that actually p naught prime is less than 0. Right? We consider that. Now you can clearly see by considering the superposition of the two effects, one the plate moving and one the pressure gradient in the z direction. So wave were not moving at all, right, then the velocity profile would be parabolic. You can easily verify that the maximum would be reached at the center line, right? So that's what the case. Then, because then wave is not moving, the atmospheric condition will make the velocity 0. You can easily find what the maximum, this is h by 2 center line. This will be the velocity profile for u equal to 0. On the other hand, v naught prime equal to 0. Then and u, let's say, is greater than 0, then the velocity profile would look like this. Then this term would be 0. You have a linear velocity profile where the velocity is linearly increasing from 0 to value of u at the top plane. So we will first consider case 1 to be u greater than 0, where both v naught prime and u are not 0, and then v naught prime is less than 0 and u is greater than 0. Let's consider that case. If you look at this, right, so you can see that if you take this as the base, ux by h, v naught prime is less than 0, so minus v naught prime is greater than 0. So both terms are positive, right? If you look at it, either suppressing this and this, or suppressing this and this, you can see that velocity is going to increase at any point between 0 and h. At 0 and h, the velocity is constrained by the boundary condition, no slip condition. So we can then ask what would be, where would the maximum of the velocity be reached, right? So you can easily show that the maximum of the velocity is reached x at z max. Then we have seen that for the case when p naught prime is 0, there is no maximum. It is linearly increasing. It reaches the maximum at the top of the plane, but it's not like that. The derivative would vanish. There's nothing like that. Here, of course, there is at h, x equal to h by 2. So when both effects are present, then the by 2 plus this. So if u is greater than 0 and minus p naught prime is also greater than 0. So the point of maximum is going to move away from the center line towards the top plane. Right? You can also find what the maximum velocity is going to be, and it is clearly going to be greater than u. That can be easily verified because it is undergoing a maximum. So what would happen then, the velocity profile, is that it will increase, and then let's say this is u, right? It's going to increase and then reach a maximum at a point somewhere, right? And then come back to, this is going to be shifted like this. So here it is 0. Here somewhere it is going to reach a maximum. That x value is given by that. Now as we can now consider the case where if is equal to h by 2, then the maximum would be reached at h, right? So this would be, if this is true, then h, and so as this ratio, right, goes on increasing and finally reaches h over 2, right, then you will see that the maximum would be reached at the top plane itself, right, but it has to reach the value of u, so the velocity would become u then, and so then that profile would look like this. It will reach a maximum flatness at, so this is the case corresponding to this condition. It will call this condition 1. Right? So you can work out all of them. I'm just going through very briefly. This is for condition 1. And of course, if this becomes greater than h by 2, this is less than h by 2, obviously the maximum would be within the plane. And when it is equal to h by 2, that quantity, which is the viscosity times the ratio of u to minus p naught prime to h, if that equals h by 2, then velocity position of the maximum will be exactly at the plane. After that, the maximum would be reached beyond the plane. I mean, if you just substitute, you're going to get a value greater than h. What that means is that there will be no maximum at all. And so the velocity profile for condition, let's say 2, when greater than h by 2, can be called condition 2, then the profile will simply increase on and down again. There won't be any maximum. It will simply reach the velocity u at the plane that you can draw. I don't want to further clutter the board. The interesting case is obtained further when we consider the case 2. Right? So let's consider the case 2. When minus p naught prime is greater than 0, but u is actually less than 0. Again, the answers would depend on the relative value of u and p naught prime, the relative magnitude. But we can argue that for at least for a certain values, you will get a profile. Now, so look at this. This is the plane. The distance is the bottom plane. This is the top plane. So we know the velocity here is 0, right? The velocity here is has to reach u, right? So if it is possible to show that the certain values of u and p naught prime, you can easily find out that condition, for which velocity must start with being positive. So certain values can be entirely negative to begin with this. So those conditions you can easily reach. What I will do is I put all these different conditions and put it in an assignment sheet and give it to you on Tuesday, so that you can derive and prove for yourself all these features. There might be more actually that I have missed out. Right? But the point here is that it's starting out like this. Right? So this is 0 velocity time. So if it has to reach the negative velocity at the top, then it has to become 0 somewhere in between. The flow reversal has to take place somewhere within the plane, and that point can also be easily figured out. Right? So it will be positive up to a certain point. Then it has to reach here, because I was fixing the boundary and guessing what the profile should be. You can get all these results by doing the actual calculation, and some of them will depend on again the ratio u by p naught prime. Here both u and p naught prime are negative, right? So then it would have to reach, and so this the point at which this will be positive, probably reach a maximum somewhere in between. And then it will reach a value of 0, it will turn around, right? That value is 0, and then it will become negative actually after a certain distance x, right? And that formula I have, so x at z equal to 0 is given by h minus 2 by p naught prime h. This is the one. Now to compare this is simply, this one is still valid, that equation is still valid, right? But only thing you have to note is that here u would be negative. The same equation is, I can write it here, because that simply depends on making dvz by dx equal to 0. You can easily show that d square dz by dx square will always be less than 0 provided p naught prime is less than 0. So we are not changing that condition. It will be independent of u. All these you can easily prove with S2. That remains as it is, but the only difference now, whereas here, when u is greater than 0, the position of the maximum, we have to, the base case is when u is 0. When u is greater than 0, the position of the maximum is going to go above the center line. You can easily verify that here, since both u and p naught prime are negative, that means minus p naught prime is positive but u is negative, this will be clearly less than h by u. And not only that, this happens at half the distance of this. Right? This happens at half the distance, because you can clearly see if I take half of this, I simply if we take half of this,
u is negative.
That's a negative sign. Yeah, but there's a minus p naught. So if you take half of this, I'm getting this. So that is consistent with this. The maximum is actually reaching, quickly make this the maximum rate will be at below h by 2. That much qualitatively I can get. The actual value you have to calculate, right? So it is going to reach the 0 value at twice this distance and then reach a u which is negative here. This will be the form of the velocity. So again, we can consider various combinations of this u over this group of term and see what is going to happen. Maybe in some cases the velocity can also find the value at which because here part of you can also see clearly for certain ratios of u over p naught prime, you are going to get positive from a certain region and there is going to be flow reversal. Positive for certain range of values, you will get a flow reversal right from the start, the bottom of the plane. Those things you can easily derive. But another perspective is obtained by calculating the total flow rate. That is something we can calculate even for the falling film, right? So the mass flow rate is given, its general formula is this. The advantage of this formula is it can be applied for arbitrary shapes of the surface through which the flow is taking place, right? So now how to apply it here, right? Here it is very easy to apply because the flow is across a coordinate plane actually. Otherwise, as I said, the dA you have to take care of properly. We know how to calculate the normal for any surface, right? But dA we will handle it once we cover a part of the curvilinear coordinate systems, right? So in this case, P is equal to Ez. So we are assuming one-dimensional flow. Now if we consider any cross section, because there's no dependence on Z, so I can consider any cross section depends entirely on X, right? So I consider any cross section, so who is going out, I can calculate the Fx, right? And clearly the outward normal would be also along the Z direction. So that would simply be N is also Ez. Right? Now dA very clearly, so whenever you have the normal of an area along a coordinate direction, then you know that the dA would correspond to a coordinate plane. Clearly that coordinate plane here is xy plane, right? So this would be equal to dz, Ez dotted with dz, so this would simply be dz, dx, dy, right? And let's assume a bit y, w, and so this would be 0 to h. We know what the formula for dz is, of course, a function only of x, so this would be w times. If we know the formula for dz, you can substitute it and do the integration fairly straightforward. The answer you will get is Now I'm going to write for the volumetric flow rate. This is the mass flow rate, right? But if I divide by rho, I'll get the volumetric rate. The volumetric rate per unit bed is given by, I'm just writing this formula. You can easily prove it plus right. So now this is general. Not real. This is a general formula. It doesn't depend on what the values of u and p naught prime are. But now you consider the case where u is greater than 0. That's an uninteresting case. If u is greater than 0, anyway, p naught prime, we've already said we are going to stick to less than 0. Both are positive, right? Both the conditions, both the terms are positive. So the flow, obviously, both the gradient, pressure gradient as well as the top weight are pushing the flow in one direction only. However, for the case when u is less than 0, right? This case 2, this will be negative and this will be positive, right? So we can easily find out the condition under which. So what that means is that part of the, cross section there is the flow out, and part of the cross section there is a flow out in the flow direction. The other is in the reverse direction. This is what is called the reversal of flow. So you can clearly see that when u is equal to minus of minus p naught prime, okay, just make it p naught prime. This applies only for the case when u is less than 0. So u is less than 0, p naught prime is also less than 0. And the magnitude of u becomes equal to the magnitude of p naught prime h squared by 6 mu. Then we see that net flow would be 0. So after that, when u becomes greater than that, then clearly, right, when u, so you can easily see that when u becomes greater than that value, then there will be a total reversal of, this is an overall, it doesn't take it upon what part the flow is in the flow direction, the positive z direction, what part it is in the, it gives the overall flow. So you get another condition, the overall flow net you collect in the positive direction is going to be positive, then you would have to be less than this. Rather, when you look at it as a magnitude, the magnitude of u, because u is negative, right? So we have to be very careful. This is also negative. The magnitude of u, right, is less than this. Then there will be a flow in the positive, net flow will be the positive z direction, but when u becomes equal to this, right, then there will be a net zero flow in the sense that, part of the fluid will be in the u is 0. What does it mean? Because volumetric flow rate is actually regarded as a scalar, but what it really means is that there is some fluid flowing in and there is some fluid flowing out at any cross section. If you look at it at a cross section, so there is some, maybe best is to look at it like this. In this part, the fluid is flowing in and some fluid is flowing out. So you can ask what is the net fluid. Right? So when u is equal to 0 means as much fluid is coming in that is going out to part of the cross section. Beyond that, there will be net fluid that is going out of any cross section. That's what it means. Right? So you can look at some interesting cases. I don't know how practically useful these various conditions are, but the fact that now you have two competing effects. U on the one hand, when it is greater than 0 and minus p naught prime is less than 0, both are acting together. So it doesn't cause really much interesting features. But when the two are competing, you get some interesting phenomena, right, which can all be derived quite easily. So I put these results, ask you to prove some of these, the various conditions and so on in the assignment sheet. So right now you should not worry too much about this. Are there any questions?
So in the bottom plate moving in the negative direction.
No, that we are not considering. But, relatively, you can say that, by keeping one plate fixed, you are only considering effectively the relative motion. That's why you are not moving everything, right? That will make the analysis more complicated. So we keep something fixed. As I said again, minus P naught prime. Why don't we consider it greater than 0? It does not require actually. I keep minus P naught prime fixed and consider two possible variations of Q. So all phenomena will be covered. Either way, yes.
Can we say the center line, the velocity will be 0 when net mass flow rate is 0?
So that I don't know. I mean, you cannot. I don't have all the results. You can calculate all of it. That's what I'm saying. I'm only giving some broad pictures of phenomena. Particular results you can actually obtain. What position, what will be happening, and how the actual velocity profile will be looking at those conditions. Velocity profile we have got is here, and so I have to go and substitute this, and then I can get how the velocity profile would look like. We have most of the expressions are there, the various conditions are there. What will happen when Tz becomes 0 at the point at which this is like the overall phenomenon flow, not focusing on particular aspects of the velocity profile, but an overall flow rate. Yes. Yeah, Q is defined like Q can be defined as 1 over rho. This is really appropriate for an incompressible fluid because rho is constant. I don't really know whether the volumetric flow rate, how we would look at it for a compressible fluid. But clearly here, mass flow rate and volumetric flow rate are simply related. One is divided by rho. So this is what I mean by Q. Right? Because of a common way of writing Q as rho V1 A1, that obviously means that the velocity is uniform across the cross section. It's a very special case of the this general formula. So the real power of this formula you will see when you getting multi-dimensional flows and the area is not very well defined. Then you will see how to actually use this to calculate the volumetric flow. Normally we not only consider well-known in the rectangular channels or cylindrical channels, but often we consider only one-dimensional flow. It's very easy to infer what the formula for the volumetric flow rate would be. This is the general formula. Right? Any other questions? Okay, if not, we will move away from rectilinear coordinates and see how to look at what are known as curvilinear coordinate systems. What we are now going to consider are non-linear transformations of the coordinate system. So in all of this, we will take the basis as our rectangular Cartesian coordinate system, which in 3 dimensions would be this. This would be the basis with respect to which any other transformation would be defined. So all the relations that we have obtained so far are going to be remain very useful, right? Because that is not to be dispensed with. Any coordinate system I look at, as we have already considered, I choose one and then consider rotation of it. Now we are going to consider slightly more complicated transformations of the rectilinear coordinate system, right? So now, in any coordinate system, we consider only 3 dimensions here. Okay, we are not going to arbitrary n dimension. three dimension, there are what are known as coordinate lines and coordinate surfaces. So there are three of them. The three coordinate lines in three-dimensional space and three coordinate surfaces. For instance, here, right, we have the rectangular Cartesian, we have the O1 line, O2 line, and O3 line. Coordinate surfaces, right, are clearly the planes, right? The planes would be 102, 103, and 203. Any coordinate system will also have this feature. You have to look at it this way. You look at it only as in terms of coordinate lines, right? But now we need a way of mathematically representing the coordinate lines and the coordinate surfaces. When you go to curvilinear coordinates, that will become very important. So Cartesian, how would you represent the coordinate line O1 line? X-axis is fine. I want a mathematical equation. Y equal to 0, Z equal to 0, or Y equal to a constant, and Z equal to a constant. Because this is the coordinate line, this is one I have fixed. All lines parallel to this are also coordinate lines, but I have to choose one finally. Because when I fix the origin, that becomes the coordinate line, right? So basically, the important thing to remember is that if I have a plane, a two-dimensional plane, which we are very familiar with, this is two-dimensional. Now I am focusing on two-dimensional. If I want to define a line or any curve for that matter, right, I need one constraint to fix the line, right? For instance, the simplest is x1 plus x2 equal to 1. So I need one constraint. It can also be a curve, it can also be non-linear. x2 equal to x1 squared. That's also a curve. One constraint will define a curve. So I have two constraints, right? x1 equal to let's say x1 naught. So what will happen? What is that? It is a point, right? So with one restriction, I get a line in two-dimensional space, but two restrictions, I get a point. The same thing now you can see, now we are in three dimensions. So to get a line, I need two restrictions. That would be the general equation of a line. Namely, the O1 line is given by x2 equal to constant and x3 equal to constant. So only x1 is changing along the O1 line. And so when the O2 line would be x1 equal to constant and x3 equal to constant, and this would be x1 equal to constant and x2 equal to constant. So when you come to a surface, there is two dimensions, there is only the plane. So you can't really consider a surface. Surface is the plane itself. The whole space is just a planar surface. When we come to three-dimensional, we can consider various forms of surfaces like planes and curved surfaces and so on. I already know the surface of the cylinder is curved, the surface of the sphere is curved. Right? We need one equation. If you get one equation in a three-dimensional space, we get an equation of a surface. Right? So what is the one equation for 102 plane? It would be x3 equal to a constant. x3 equal to 0, we get the coordinate plane that we finally choose. But all planes parallel to it are also surfaces, right? So 103 would be x2 equal to constant and it would be x1 equal to constant. Now, when we go to curvilinear coordinate system, the form of the coordinate lines and coordinate surfaces will remain the same, but they now have to be expressed in terms of the new coordinates variables that we are going to choose. We discussed that in class next week.